careful is his first name. He is a molecular physicist that turned into the dark side and went to history of physics. And he's working in history, very interesting stuff, at the Fritz-Haber-Institut of the Fritz-Haber-Institut of the Max-Planck-Gesellschaft in Berlin. Okay. Is it working already? Almost there.
Thank you very much for installing the presentation. Thank you very much for inviting me. Thank you very much to Sophie and to Valen for the excellent analysis received so far. Thank you for the introduction. Yes, sorry. I'm going to switch gears a little bit. Let me start by saying that the discovery of quantum mechanics, widely regarded as a prime example of a revolution in science, had its experimental side, now largely neglected in textbooks as well as in the celebratory events of the International Year of Quantum Science and Technology. Experiments played a key role on the path to quantum mechanics. In this talk, I will mention only some, not all, of the many experiments that had to do with the emergence of quantum mechanics. In fact, I will concentrate on just two: the astrophysically discovered spectrum of helium plus and the Stern-Gerlach experiment. These two represent qualitatively different aspects of the contribution of experiment to the quantum revolution. These iconic images on this slide showcase the mounting experimental evidence for the emerging quantum mechanics. You can read actually what they are. Let me just note that including among the icons is the spectrum of atomic hydrogen, representing the clues provided by spectra, whether obtained in the laboratory or via astrophysical observations. This is the timeline of some of the key discoveries in physics that preceded and followed upon the advent of quantum mechanics. The advent of quantum mechanics can be clocked in terms of the comings of Planck's constant, a word appropriate perhaps in the Holy Land to use, shown in white. The forthcoming was in Bohr's model of the atom, which then became an embodiment of much of the so-called old quantum theory. The spectrum of helium plus served as a proving ground of Bohr's model, boosting its credibility. On the other hand, the Stern-Gerlach experiment was devised by Otto Stern to disprove Bohr's model and its amendments, and with it to bring about the demise of the old quantum theory. However, despite its intended purpose, the Stern-Gerlach experiment ruled unequivocally in favor of Bohr's model. As a result, Otto Stern became an involuntary convert to quantum theory. After the introduction, which you have just endured, I will provide a very brief summary of Bohr's atom model before discussing the spectrum of helium plus, the Stern-Gerlach experiment, and Otto Stern's involuntary conversion. That optical spectra uniquely label chemical elements found on Earth or in stars was at the core of Gustav Kirchhoff's and Robert Bunsen's foundational work in spectroscopy, which began in the 1850s. However, understanding where the unique spectral features originate came only with the Bohr model of the atom about 60 years later. As Bohr himself put it, in those early days, spectra were as interesting and as incomprehensible as the colors on a butterfly's wing. Two key experimental discoveries preceded Bohr's model of the atom, the discovery of the electron and the discovery of the atomic nucleus. Interestingly, and this is a somewhat technical point, but nevertheless I think a very important one. Interestingly, in his paper on the discovery of the atomic nucleus, Rutherford did not commit to whether the nucleus was positively or negatively charged, although he knew perfectly well that the alpha particles scattered by the gold foil were positive. Apparently, this was because Rutherford understood well enough what we call today Rutherford scattering, that is scattering by the Coulomb potential. The point is that for scattering by the Coulomb potential, the angular distribution, the differential cross-section of the scattered particles is the same for an attractive and for a repulsive interaction. Rutherford was careful not to claim more than his experimental results could support. One of the rarely mentioned virtues of Rutherford's model was that it separated the electrons in the atomic shell from beta rays, which are electrons emanating from the atomic nucleus. Well, enter Niels Bohr discreetly to propose a quantum model of the atom. I misspoke before, I meant Rutherford's model. Bohr's model incorporated Rutherford's planetary constitution of the atom, the Ritz combination rule for transition frequencies or wavelengths, and Einstein's light quantum hypothesis. For the stationary states of the orbiting electrons, Bohr introduced a new ad hoc hypothesis about the electron's angular momenta, which he did not even try to explain. This slide summarizes the triumphs of Bohr's model of the hydrogenic, that is, one electron atom, the expression for the Rydberg constant, Rz, in terms of fundamental constants, and the unriddling of the Balmer series, discovered by Johannes Balmer in the 19th century. However, the Bohr model and thus the unriddling were based on the above-mentioned unjustified ad hoc hypothesis. Niels Bohr was fond of telling the following story. One of the visitors to his country house in Tisvilde noticed a horseshoe hanging over the entrance door. Puzzled, the visitor turned to Bohr and asked him whether he really believed that this brings luck. Of course not, Bohr replied, but I'm told it works even if you don't believe in it. The old quantum theory was much like that horseshoe above the door. Somehow it worked even if you didn't believe in it. Let me now cut to the chase and talk about the astrophysical discovery of the spectrum of helium+. In October 1896, while inspecting spectrally resolved astrophotographs of the southern star Zeta Puppis, Wilhelmina Fleming noticed a peculiar spectrum of an element not yet found in other stars or on Earth. At the time, Wilhelmina was one of the computers working at the Harvard College Observatory in Cambridge, Massachusetts. The director of the observatory for the previous 19 years was Edward Pickering. The day of the discovery of the unknown element is recorded in Wilhelmina's logbook along with the wavelengths of the unknown element's spectral lines. Also recorded are the wavelengths of the omnipresent Balmer series of atomic hydrogen, which served as a frequency standard. The discovery of the as yet unknown element via its peculiar spectrum was rushed to the printing press and published already 4 days later as a circular of the Harvard College Observatory. At the same time, with slight modifications, the paper was submitted to Astronomische Nachrichten and the Astrophysical Journal. Apparently, the notion of self-plagiarism had not yet been invented. All 3 papers were published under Pickering's name only, although the first sentence of each of them acknowledged that it was Wilhelmina Fleming who discovered the spectrum. Because of Pickering's sole authorship of these publications, the spectrum of the unknown element became known as the Pickering series. Let me say a few words about how Wilhelmina discovered the Pickering series. The spectrum of the southern star Zeta Puppis with all the riches encoded in it was not obtained at the Harvard College Observatory in Cambridge, Massachusetts, but rather at the observatory's southern station in Arequipa, Peru. The method used was spectrally resolved astrophotography. The astrophotographs were developed in Arequipa, shipped to the Harvard College Observatory in Cambridge, and analyzed by the human computers there. In astrophotography, light collected by a telescope was dispersed by a system of prisms and recorded on a photographic glass plate exposed over a well-defined time period. Astrophotography revolutionized astronomy in several respects. Apart from including spectral information, it provided a permanent record of an observation made at a particular time that could, moreover, be evaluated in daylight. Wilhelmina is shown here on the right using a special frame backlit by a mirror, which allowed her to view the images on the glass plates. This is a photo of the glass plate with a peculiar spectrum of Zeta Puppis along with its jacket. The label X identifies the 8-inch Bache telescope used to collect the spectrum. The spectrum is just a smudge. The trio of the 1896 papers pointed out that the formula of Balmer will not represent the Pickering series, but went on to show that when suitably modified, a formula involving squares of an integer pertaining to the individual lines fits the spectrum. Fudging spectral formula was very much in the spirit of the times when physicists were groping for the conceptual foundations of spectroscopy in the absence of a physical derivation of a formula for the Balmer series or any other. Now a dash to 1913 Copenhagen. In an addendum to his 1913 trilogy on atoms and molecules, Niels Bohr showed that the unknown element in the spectrum of Zeta Puppis was in fact ionized helium, helium plus. By applying his theory of the one-electron atom to helium plus, Bohr was able to render the Pickering series with an astonishing 5-digit accuracy. The Pickering series thus served as a proving ground for Bohr's model of the hydrogenic atom. According to the metaphor introduced by Michel Janssen, Bohr's atom became the scaffold for building the cathedral of quantum mechanics. As we already noted, according to Bohr's atomic model, the wavelength of an emission line of a hydrogenic atom with nuclear charge Z was given by this formula, where Rz is the corresponding Rydberg constant. The ratio of the Rydberg constants given by Bohr's formula for helium plus and for atomic hydrogen would then come out exactly as 4, right? To the 2 to the power of 4 over 1 to the power of 2 to the power of 2 over 1 to the power of 2 is equal to 4, exactly. Upon reading Bohr's trilogy papers, Alfred Fowler of Imperial College London pointed out to Bohr a discrepancy between Bohr's treatment of the Pickering series and the positions of the spectral lines of the series as measured in his own laboratory and confirmed in Rutherford's laboratory. This is the experimental value of the ratio as obtained by Fowler, 4.0016, not 4. Fowler thus concluded that Bohr's model cannot be right. Whereupon Bohr went back to the drawing board and replaced in his expression for the Rydberg constant the electron mass with the reduced mass of the nucleus electron system as he should have done to begin with. This amendment gave the ratio for the Rydberg constants of 4.00163. The explanation of the Pickering series was a major triumph for Bohr's theory. Thereby, Bohr's model of the atom proved capable of not just reproducing the well-known and well-established, such as the Balmer series or the Rydberg constant for hydrogen, but it also demonstrated its predictive and explanatory power. In particular, the accurate rendition of the ratio of the Rydberg constants for helium plus and hydrogen made a deep impression. When Albert Einstein heard about it from Georg von Hevesche at a conference in Vienna in late 1913, he exclaimed, according to von Hevesche, "Then the frequency of the light does not depend at all on the orbiting frequency of the electron. This is an enormous achievement. The theory of Bohr must then be right." In his penultimate paper published in Science in 1951 and entitled The Advent of the Quantum Theory, Einstein took the opportunity to pay tribute to Bohr's model once more. He called its discovery the highest form of musicality in the sphere of thought. However, not everybody was impressed by the triumphs of the Bohr model. Otto Stern and his close colleague and friend Max von Laue even took a vow: if this nonsense of Bohr should in the end prove to be right, we will quit physics. The so-called Uetlischwur. Otto Stern would go further yet and devise in 1920 an experiment to disprove the Bohr model of the atom. This experiment is known as the Stern-Gerlach experiment. In 1916, the Bohr model was independently amended by Arnold Sommerfeld and his former PhD student Peter Debye. As a result, by the time Otto Stern conceived the Stern-Gerlach experiment, that was in 1920, the old quantum theory was epitomized by the Bohr-Sommerfeld-Debye model of the atom. The Bohr-Sommerfeld-Debye model entailed quantization of the magnitude and projection of the orbital electronic angular momentum and of the eccentricity of the electron orbits. The quantization of the magnitude and eccentricity of electronic orbits was arguably manifest in atomic spectra. However, the quantization of the projection of the orbital electronic angular momentum, that is the so-called space quantization, stood out as the so far untested feature of the Bohr-Sommerfeld-Debye model. Stern singled out space quantization and undertook to determine whether it existed or not. If the existence of space quantization was confirmed, so would be the quantum atomic theory embodied by the Bohr-Sommerfeld-Debye model. That was the thinking. As Stern put it, the experiment would decide unequivocally between quantum theoretical and classical views. So let me now talk briefly about the Stern-Gerlach experiment. The laboratory that Stern and Gerlach used for their one and only joint experiment was part of, remarkably, the Institute of Theoretical Physics of the University of Frankfurt. The institute was headed at the time by Max Born, who apparently did not quite believe in the separation of physics into experimental and theoretical, and indeed took part in some of the measurements. Stern realized that space quantization of angular momentum would have observable consequences. Even an external magnetic field H, which defines a space-fixed axis Z, space quantization of the angular momentum vector L means that only discrete values Lz of the projection of the angular momentum on the z-axis occur or are allowed. In other words, if theta is the angle subtended by L and Z, then cosine theta is equal to an integer m. Now, Otto Stern realized that the magnetic moment mu, shown in red, due to the orbital motion of the electron, would then be space quantized as well, that is, only take a discrete set of values given by the projection quantum number m. In particular, for one quantum atom, that is an atom whose only unpaired electron possesses just one quantum of orbital angular momentum, L equal to 1, and thus m equal to plus minus 1, the only possible values of the magnetic dipole moment will be plus minus one elementary quantum of magnetism called Bohr magneton, mu b. In an inhomogeneous magnetic field of a given gradient, the one quantum atoms will be subject to a force whose components will impart equal but opposite deflections along and against the direction of the magnetic field gradient. Here's how Stern described the contrast between what this force will do to the atoms in a classical and a quantum mechanical case. If the deflection of the atoms is greater than the spot size, the cross-section of the atomic beam, there must be a minimum intensity of the position of the original spot, where the beam would be hitting without the magnetic field. Exactly the opposite follows from the classical theory. The spot on the collection plate would only be broadened, but its maximum intensity would always remain at the location of the original spot. In this way, the experiment, if successful, would unequivocally decide between the quantum theoretical and classical description. Stern calculated that for silver atoms that he had worked with before, the deflection on a path of length of a few centimeters to a magnetic field with a gradient of 1 Tesla per centimeter will be on the order of 10 micrometers, that's 10 small. At which point Stern realized that he would need to team up with a real experimentalist, as he put it, in order to get this experiment done. The experimentalist Stern joined forces with was Walter Gerlach from the adjacent Institute for Experimental Physics. The collaboration between Stern and Gerlach was a stroke of luck, not only for the Stern-Gerlach experiment, but, given its significance, for physics at large. It brought together Stern's out-of-the-box thinking, Querdenken, with Gerlach's skills and tenacity in the laboratory. Stern credited for his way of thinking his apprenticeship with Albert Einstein during their time together in Prague and later in Zurich. Gerlach became a major player in experimental physics already when he was a PhD student in Friedrich Paschen's laboratory at the University of Tübingen. His training by Paschen proved formative for both Gerlach's personality and his experimental abilities. Either became a key prerequisite for the success of the Stern-Gerlach experiment and other precision measurements where Gerlach pushed the limits of the possible. Now that Stern posed his momentous question to nature, namely, will there be just a broadening of the beam of silver atoms or a splitting of the beam into two, Stern and Gerlach set out to tease out nature's answer. I will spare you the experimental details, although they are quite interesting. Let me just show you this photo of the Stern-Gerlach apparatus, which evolved over 3 generations of improvements before the Stern-Gerlach experiment came to a successful conclusion. The effort needed in order to make the experiment work was tremendous. Moreover, it was mostly the result of Gerlach's lonely toil, as Stern, who did not believe in the reality of space quantization to begin with, left in October 1921 to assume a professorship in theoretical physics at the University of Rostock. On his way back from a meeting with Stern in Göttingen in February 1922, Gerlach recollected a modification he had made earlier when examining crystals by X-rays using the Debye-Scherrer method, namely to use a slit instead of a pinhole to boost both flux and spatial resolution. And so, upon his arrival in Frankfurt, Gerlach replaced the pinhole defining the silver beam at the entrance into the magnetic field by a rectangular slit. Then during the night, from the 7th to the 8th of February 1922, Gerlach then achieved the ultimate success. This is a postcard Gerlach sent on the same day to Niels Bohr. We congratulate you on the confirmation of your theory. Interestingly, based on Stern's correspondence, Niels Bohr was the only colleague with whom Stern was erdu on first-name basis. Gerlach and Stern published what they saw as the main results of the Stern-Gerlach experiment in 2 installments. In their paper, The Experimental Proof of Space Quantization in a Magnetic Field, they reported their epochal discovery. In the second paper, they presented their conclusion that the measured magnetic dipole moment of the silver atom was 1 Bohr magneton. This conclusion was true only approximately and, moreover, on account of what could be called an uncanny conspiracy of nature. For as we know today, the silver atoms were in their electronic ground state doublet as 1/2. Thus, their magnetic moment was due to electron spin. The components of the magnetic moment along the magnetic field had a magnitude given by the product of the electrons' gyromagnetic ratio of about 2 with a spin quantum number of 1/2, which approximately cancel out each other, and then the up and down magnetic moments appeared to have a magnitude of about 1 Bohr magneton. The absence of the concept of electron spin confused and confounded the interpretation of the Stern-Gerlach experiment. However, a key quantum feature whose existence the Stern-Gerlach experiment was designed to test, namely the existence of space quantization of electronic angular momentum, was robust enough to transpire independent of whether the electronic angular momentum was orbital or due to spin. The reception of the outcome of the Stern-Gerlach experiment was that of astonishment, as illustrated by the individual reactions that I'll now show you. Let's begin with Isidor Rabi. In 1927, Isidor Rabi came to Europe as a Barnard, later Rockefeller Fellow, and worked intermittently with Sommerfeld, Heisenberg, Bohr, and Pauli, the last based in Hamburg, where Rabi also met Otto Stern. Stern moved namely to Hamburg from Rostock in 1923 and established a molecular beam laboratory there, to whose lures Rabi quickly succumbed. Here's what Rabi said. As a beginning graduate student back in 1923, I hoped that with ingenuity and inventiveness, I could find ways to fit the atomic phenomena into some kind of mechanical system. My hope to do that died when I read about the Stern-Gerlach experiment. The results were astounding, although they were hinted at by quantum theory. This convinced me once and for all that an ingenious classical mechanism was out and that we had to face the fact that the quantum phenomena required a completely new orientation. Walter Gerlach noted, the proof of space quantization was the first experiment that made an atomic state predicted by quantum theory accessible to a direct measurement as opposed to a spectroscopic measurement that actually always uses two states. In his letter to Gerlach, Friedrich extolled the significance of the Stern-Gerlach experiment for quantum theory. Your experiment proves for the first time the reality of Bohr's atomic states. In keeping with this implication of the Stern-Gerlach experiment, Wolfgang Pauli quipped, "This should convert even the non-believer Stern." And it did. In a 1961 interview, Stern said, "By the way the experiment turned out, I didn't understand at all. It was absolutely impossible to understand. This is also quite clear. One needed not only the new quantum theory, but also the magnetic electron. These two things weren't there yet at the time." Now comes the punchline. "I still have objections to the idea of beauty of quantum mechanics, but she is correct." The first published reaction came from Stern's mentor, Albert Einstein, who in the wake of the Stern-Gerlach experiment teamed up with Paul Ehrenfest, only to express more puzzlement about the workings of the Stern-Gerlach experiment. We add that although Gerlach ended up doing the experiment mostly by himself, Einstein and Ehrenfest coined the term Stern-Gerlach experiment rather than Gerlach-Stern experiment in recognition of the fact that the experiment was Stern's idea. One may wonder why the value of the projection quantum number n equal to 0 was left out of Stern's original considerations. There doesn't seem to be a clear answer. However, after the completion of the experiment, Niels Bohr offered in a letter to Gerlach to put his mind to it and explain it. We note that the L equal to 0 value of the orbital angular momentum was excluded from the Bohr model as it would lead to the collapse of the atom. Not everyone was unfazed by the outcome of the Stern-Gerlach experiment. Stern's and Gerlach's Frankfurt colleague, Alfred Landé, who had worked on unriddling the anomalous Zeeman effect since 1919, provided a prescient interpretation of the Stern-Gerlach experiment based on his understanding of atomic structure and on the G-factor that he had introduced. Landé would treat the Stern-Gerlach experiment as a manifestation of the anomalous Zeeman effect. After all, it was the number mystery, according to Sommerfeld, or number misery, according to Pauli, of the anomalous Zeeman effect that led Sommerfeld and Debye to introduce the notion of space quantization in the first place. Thus, unlike Bohr, Sommerfeld and pretty much everybody else, Landé would not be fooled. He noted that for L equal to 1, the silver beam would be split into 3 beams corresponding to m equal to -1, 0, and +1. However, since a splitting into only 2 beams was observed in the Stern-Gerlach experiment, Landé concluded that the silver atoms must have been in a doublet state with L equal to 0, and his core quantum number, which he called R for Rumpf, 1/2, and projections ±1/2. The magnitude of the deflection would then be just 1 In 1944, 11 years after his forced emigration from Germany, Otto Stern was awarded the 1943 Nobel Prize in Physics unshared. The official number of nominations provided by the Nobel Archives for Otto Stern is 82, more than any other physics Nobel laureate on public record. Stern would share the stage with Isidor Rabi. The ceremony took place under war conditions in the Waldorf Astoria Hotel and was administered by the Swedish Foreign Secretary Volmar Boström. He is a quote by Rabi, who considered himself to be a pupil of Stern's. From Stern and from Pauli, I learned what physics should be. For me, it was not a matter of more knowledge, rather, it was the development of taste and insight. Stern had this quality of taste in physics, and he had it to the highest degree. Remarkably, FDR was also delighted by the Nobel Prize for Stern. Stern would become an American citizen in 1939. The legacy of Stern's and Gerlach's molecular beam work in general and of the Stern-Gerlach experiment in particular is aptly reflected in the physics Nobel Prizes awarded so far for work in atomic, molecular, optical, chemical, and even gravitational physics. This is illustrated in the list shown on this slide of the 26 Nobel laureates scientifically related to Rabi, Stern, and Gerlach. Ironically, much of quantum mechanics as we know it is embodied in the Stern-Gerlach experiment, whether quantum measurements, state preparation, coherence, or entanglement, apart from the quantization of angular momentum and spatial projections. The Stern-Gerlach experiment has it all. Moreover, its conceptual clarity has made it a quintessential prototype for our thinking about quantum systems and the quantum classical correspondence. From the Stern-Gerlach experiment unfolded novel perspectives as well as wide-ranging and far-reaching applications. Here's a partial list. Among the most recent additions to the list is the Stern-Gerlach interferometer. The Stern-Gerlach interferometer was considered impossible to realize because of the requirement of a reversible Stern-Gerlach splitting. In 1988, Julian Schwinger and co-workers likened the passage of the atoms through the Stern-Gerlach magnet to the Great Fall of Humpty Dumpty and concluded, in agreement with Lewis Carroll, that one couldn't put Humpty Dumpty together again. However, in 2019, none other than Ron Folman and co-workers proved such skepticism wrong and demonstrated that Humpty Dumpty can be put together again if all its pieces are matched accurately enough. The Stern-Gerlach interferometer that ensued can be used to test aspects of quantum gravity, as we heard today from the horse's mouth. So, looking at the whole list, perhaps it's appropriate to paraphrase the well-known statement about the steam engine and thermodynamics. Quantum mechanics owes more to the Stern-Gerlach experiment than the Stern-Gerlach experiment to quantum mechanics. I'm almost done. Let me conclude with two remarks on the role that experiments played along the way to quantum mechanics. Most of the experiments that lined the path to quantum mechanics amounted to a backlog of data in need of explanation. The spectrum of helium plus is a good example of that, a part of the pile. However, the Stern-Gerlach experiment was different. It was devised to test whether the assumptions of quantum theory as embodied in the boson-Felderbye model were correct or not. They were. Let me add that in 1933 and following years, Otto Stern did it again. He tested Dirac's so-called Hole theory, H-O-L-E theory, of the proton by measuring the proton's magnetic dipole moment, which turned out not to be one nuclear magneton, as Dirac's theory would have it, but about 2.5 nuclear magnetons. This upended Dirac's 1930 theoretical conclusion that the proton was a point-like particle, like the electron, but had, in fact, internal structure. In consequence, Stern's measurement of the proton's magnetic dipole moment became a cornerstone of elementary particle physics. The finding was also a vindication of the imperative that guided Stern's work, namely to test the assumptions of theory, no matter how plausible they may appear, by experiment. As the physicist Edgar Meyer put it, no experiment is so dumb that it should not be tried. Thank you.
Okay, so we have time for one or maybe two very short questions.
Yeah, it's not a question, but first of all, I really enjoyed your talk.
No, thank you.
And second, you know, popular literature always says, well, Bohr's model is completely obsolete, it's only used for educational purposes, and I think you have revived for us Bohr's model. And the other point about Rutherford, that he was so careful, he realized, of course, that his model was not stable and that there is a problem there.
Yes.
But he was very happy with the discovery of the nucleus. So he added a note saying, the stability, I set aside the problem of stability, it will probably be solved by the minute structure of that we will discover by further research. And then Bohr, 2 years later, came to this wonderful assumption. So
There was also no size. I tried to show it in a cartoon, you know, the planetary model did not have any characteristic size.
thank you.
From what I understood, your contention that Stern was unique was in the sense that he devised a unique test and was able to carry that out. Would that characterize him as a distinct revolutionary?
I would say so. Also, you know, as was noted in the previous chart, his skepticism. He didn't want, you know, space quantization to exist. He found, you know, the Bohr model was an abomination to him. And space quantization, you know, something completely incomprehensible. He, you know, started kind of grasping what it was only after the advent of quantum mechanics and, of course, the discovery of space.
Thank you very much.